The next presenter that we have up will be the SlimSat project for high schools, Nick Pugh and Bob Twiggs.
Well, good morning, everybody. This is going to be the Bob and Nick show. So I'm Nick Pugh. I'm the Raging Cajun from the French-speaking piece of Louisiana. But as most of you guys, I think we're tinkerers. You know, and you might be a tinkerer if by the time you learn to crawl, you figured out how to jam a wire into a receptacle and get yourself excited. For you youngsters in the office, in the audience, when we grew up, you know, I used to take a forklift to move a TV around. And in the TV, you know, they had a cathode ray tube that was about this long. And to accelerate a beam down that thing, it took about 30 kilovolts. Well, as a youngster, we took that thing apart and quickly found out where the high voltage was. Some of us probably built a crystal set. How many of you guys in here built a crystal set? Yeah. You know, and one of the things that we got through our careers, the first thing we did, we went into our dad's workshop, built something that caught on fire. You know, and being an engineer, we innovated that process and made a bigger fire. And some of us, most of us, I hope, got an amateur license. So our mission is to get 20 high schools and universities with almost no experience to build or design, build, launch, and operate a satellite in LEO. Now, AMSAT has got several programs, 2 or 3 of them, ours being one of them, that are kind of parallel, and we think ours might be the starter. So it's our intention, if we can get Alana to give us a launch, is that we will put 20 small satellites in orbit every year. So the way we plan to do that is we're going to take a 3U, and we're going to jam as many small mini satellites as we can get in there and release them on orbit. We're going to wait till we get below the ISS orbit, and we'll probably, if we're lucky, we'll get about a year's life out of them. But our program differs from some of the others is that we're kind of like womb to tomb. We want actually to get kids and college guys flying satellites. You know, Alan's deal, we think ours might be the starter, and then they migrate into Alan's, and then let those students build bigger and better satellites. Now, we've got some challenges, but here are some of the outcomes we want. You know, if you're going to build a satellite, it takes teamwork. And young kids and college students don't work well as teams, but to get something done, you gotta work as a team. As if you're going to build a satellite, you got to learn something about space. You got to know something about orbital mechanics. You got to know something about communications. You got to know something about how to convert sun energy into batteries, energy, and store it, and how to efficiently use it. And you're going to use and learn things about sensors. And of course, because there's radios on it, and we're just biased to be radios, we want everybody that gets on a build a satellite to become an FCC license holder. So here's some of the things we're going to tell NASA. Here's why they ought to give us the launches. First of all, it meets their education goals. This allows NASA to get 20 satellites a year into orbit. Now, we're going to pass our merit and review panels. We've got this thing fully funded. It's a big workforce effort. You know, if you get kids building satellites, most of them are going to work in aerospace. And what I always tell educators, you know, if you think you're going to collect your Social Security, you better start teaching kids how to build things. And of course, you know, we get excited. I call this the wow factor, is that once you get somebody who can brag about putting their fingerprints on hardware in space, That ought to get them excited. If they're thinking straight, this gives them a ticket for scholarships. I tell them, you want to give your parents a raise? Go get a scholarship. So let me describe what we're trying to do here. This is a very early piece of prototype. I got one I'm going to put on the table in a minute. We think we're going to build these things. They'll be 85 by 85 by 15 millimeters. We want these things to weigh less than 200 grams. We want them to be programmed in an Arduino IDE. We're going to release these below the ISS orbit. We understand all the new rules, and the FCC is not excited about licensing things that are smaller than 1U. We're going to package a 900 milliamp hour battery in there. We're going to have solar panels that are producing 2 watts per face. Now we're challenged because this thing will be flipping around. We don't know how much of that 2 watts we can actually gather. And we're going to put a peak power tracker in there. Some of the other descriptors of this thing is going to put out a whopping, we're going to power it up for 20 minutes in an orbit. We think we've got enough battery to run that transmitter for 20 minutes. It's going to put up a whopping output power of 17 dBm. Here's what is exciting to us. The sensitivity on this receiver is minus 148 dBm at 24 baud. We understand, you trade sensitivity for data rate. But if our students are smart enough, we're going to make this data rate adaptive. So as that satellite gets a little closer, we're going to crank up the data rate. Of course, we're going to put this in the UHF band 437 to 438 megahertz. Now, here's what's kind of unique about this. Because of that sensitivity, we're going to put a monopole on the end on the satellite and an omni antenna on the ground. So this makes the ground stations extremely simple. Probably a 5/8 inch vertical would probably just do really fine. Of course, we got to make this thing work from minus 10 to 50 degrees Celsius in orbit, and we got to probably shake it to 22 grams. And we're gonna fly it in the ham band, so it's going to be somebody's got to get this thing licensed. So some of the other things that we're going to fly on the payload, we're going to let the students design their own payloads. This satellite will contain a solar panel, a battery, a processor, and a radio. And the processor will, of course, have buses, I2C buses, 1 or 2 GPIOs, an analog to digital deal, and a UART. We think if we did our energy corrections right, we will have the payloads will have about 200 milliwatt hours per orbit, milliamp hours per orbit to run their payloads. We've got about 150 square centimeters of empty space for them to design their own sensors and their own payloads. We're going to have an external watchdog timer, watchdog cutoff circuit for latch-ups. And of course, we're going to build in temperature and battery and voltage sensors on for housekeeping. So now here's the link budget, and here's what's kind of exciting about it. We're going to put it in the UHF band. We're going to say that at the horizon, that's about 1,500 miles from the ground station. We're going to have an output power of plus 17 dBm. We're going to run 0 gain antennas on the satellite and 0 dB gain antennas on the ground, which gets us puts a receive signal level coming to our receiver at minus 136 dBm, and the radio will work down to minus 148. So here's a quick power budget. Our little receiver will pull 12 mils. We'll run that all the time. Our transmitter at 7 plus 17 will pull 120 mils. And of course, our processor will pull 14 mils. And we're going to allow 200 milliamp hours per orbit for payloads. So the total power consumption we're hoping to be power positive is that we will consume about 461 milliamp hours per orbit. If we miss that, we'll have to back off on our transmit time. And if we get into real trouble, we'll have to start putting some of these devices to sleep. So here's the block diagram. We are showing 16 little solar panels. Actually, the mechanical team tells me I can only get 14 in, so this is not quite accurate. We're going to put a peak power tracker on both faces. We're going to have batteries, two little coin cell batteries in there, a watchdog timer, and a Shao microprocessor. So let me talk a little bit about this radio. It's a LoRa, and I know Zach back there is going to complain because it's proprietary. But for $5 and its sensitivity, we think this is a pretty good choice. So this thing has an output power of plus 18. The sensitivity at 24 baud is minus 148 dBm. In fact, that's so low, it's very difficult for us in our little skinny lab to make sure we can get enough isolation to test the sensitivity on this thing. And of course, the modulation is a chirp sped spectrum. So it's kind of magic how this thing works. But this thing allows us to detect signals 20 dB below the noise, which is, in my view, magic. Here's a little deal why we think sensitivity is important. You know, a typical G3 RUH modem at 24 baud requires us to put a signal at the input of the receiver at minus 137 dBm. This LoRa module at the same rate will detect things 20 dB below the noise, so we only have to come in at minus 148 dBm, which is a significant improvement. And that lets us get into schools that have no infrastructure. And we have a little demo of the ground station over here. So they can go plant a vertical out in the middle of some field out there, and they've got a ground station. You know, for us who've put up Oscar antennas, that's a pretty good project for us. So here's the demo that we're hoping, we're kind of like Alan, we're keeping our fingers crossed and hope Murphy stays home, is that on the left over here is our balloon version of the satellite. This box over here, this little box in the middle is our ground station. And of course, it's tethered to my smartphone. And what we're going to demo is that this thing is now Wi-Fi'd into a server, io.adafruit server. So we have a server built in, and I'm going to switch to that in a minute. Because we can put this thing on, by the way, this thing only weighs 5 ounces, and this includes enough insulation to let that thing work at minus 50 or 70 degrees in centigrade. So we start by flying this thing on a balloon. But, and because the server's built in, you know, the kids can not only, they can walk around the parking lot and measure things. We got several sensors involved and hooked up in this thing. And so basically, guys, let's see. I thought I had a picture of it. Oh, missed. Well, gee. This thing won't let me back up. So let me switch and see, keep our fingers crossed and see if we can actually let this thing talk to this server. So this is a server picking up live data. And remember, this balloon package will talk to this ground receiver, which is tethered to my cell phone, which is then hooked to a server. So in the classroom, all the kids can see this data live. And here's some of the sensors in that balloon. So we're picking up the RSSI. We're picking up some temperature in here. And look how neat the graph is. It's all set up and done, and kids can configure their own server really quickly. So that's what we got. So are there any questions so far? Bob's going to get up and continue this talk on what he's up to. Okay, Bob, it's your turn. Oh, you got your thumb drive?
How many of you have heard of a CubeSat? Many years ago, and tonight I'll give a presentation on the kinds of satellites that I've been involved in. And a very interesting thing happened in the academic thing with myself, using satellites as a way to teach students how to build things. And it turns out that I've found out, and I'm sure you found out, once you give these kids an opportunity to get in the lab and start building something, I had a problem with them locking me out of the lab. They didn't want me in there fiddling with it. But the CubeSat come about from a fact that I had some students that were building microsatellites, and there was too much room in a microsatellite, and it was a group of master's degree students, and they only stayed in the program for 1 year, and every time a new group would come in, they would want to change everything and put more stuff in there. So I figured the best way to stop them from adding all of these things was make something so small that they couldn't put very much in it. And so we had a project where we actually used a microsat to launch pico satellites. We worked with the Aerospace Corporation and launched these pico satellites that were about the size of an ice cream Klondike bar. And it worked out pretty well, but I thought if you're going to make a little satellite, you probably should have something that's not flat like an ice cream bar. And so I started looking around for something to use for a small satellite, and I went to the local plastic store and found a 4-inch box that they put Beanie Babies in. And so I got that box, went back to my office and looked around to see if I could find solar cells that fit on it. And by golly, I could put a couple of solar cells on each side. So another professor at Cal Poly, Jordy, talked to him about it, and he says, well, let's try that. And then I made a launcher out of plastic and sent it to Jordy along with my specifications, and we decided to go there. And so Jordy proceeded with his students to get the specifications going and so on. And then we advertised it. And how many of you remember when it was first advertised? Do you remember what you said to us? We're stupid. Nobody would use anything that small. And there were not some very complimentary things said about us at that time, including you academic guys aren't smart enough to build a satellite. So what do you do when you get a challenge like that? You know, you give it to the students and they do it, right? We got a lot of comments about this is kind of a stupid idea. Do you know what the projected commercial value of the small satellite is in 2030? $6 billion. And whoever thought that? We said, we don't care what you think. We built this for education, and look it, there it is on the table, being used for education. And it is amazing. I'm working with a former student of mine that is writing a book about the CubeSat. And so we're talking to a lot of the people that got into it. And it is really interesting. I went back and talked to some of my former students, and we said, and there are a number of them that are very, very successful. There are a number of them that started out with some guy named Elon Musk, and with his rockets, getting them launched. And I talked to the students, one in particular is a young lady that's working at the Lockheed Martin advanced lab in Palo Alto. And her team is building instruments for, they build instruments for the James Webb Telescope and some newer telescopes. And we talked to her, what was the value of that program? And she said, well, it was you put us in the lab and you said we had at that time to build a microsatellite. And we had to go get all the parts, beg and borrow to get parts. And if we could, we would steal them. But she said it was working on that satellite and all the things that we had to do in terms of a group to get it to work. And I said, well, what about my classes? Well, they were okay. You know, but they learned the most in the lab, and I think that is a real lesson. That young lady now got her PhD at Stanford. She's working for Lockheed Martin and has 87 people working for her. So it really helped out. It really was an educational project. So we went on from there and worked with, early on, worked with AMSAT on the microsatellites, the 4 microsatellites that were launched. But one of the things that I have wanted to do since I retired is to get back into the grade schools and the high schools with STEM projects, because it really makes a difference in the kids. I know all of you have had that kind of experience, but you get a group of kids together and ones that said, you know, I hate school. I really hate school. By the time they work on these projects, they really learn to like school because they need all of the classes and all of the subject that they need. But one of the things that we got into is, one of the things that I found out is when the CubeSat got popular, we got pushed out from the education side because of the price of the launches. You know, we got our first launch for $30K, and we can almost have a bake sale to get $30K. But then they went up to $90K. And then, of course, NASA got in, and oh boy, did the paperwork increase. How many of you do NASA paperwork? Yeah. It's a real pain, right? When we first started, we didn't have to do all of that paperwork. But the thing that I wanted to do was get the price of getting something launched down. And so I started working on a thing called Pocket Cube. How many have heard of Pocket Cube? A few of you, huh? Now that's a really going, actually commercial business. And so I was trying to figure out with the CubeSat launcher, how could I make Pocket Cubes? And Pocket Cube is not a 100 centimeter satellite, it's a 50 centimeter satellite. And of course the guys that said you can't put anything in a 100 centimeter satellite said, oh crap, there he goes again, you know. But the thing that happened is the miniaturized components really can get some stuff that's really small. But I kept trying to find a way to get them launched, and I finally run into Warren Frick at the SmallSat conference in Utah. And I'd heard about the possibility of launching something on second stages. You don't get much orbit time. But I thought, hey, if we can get on the second stage, they said we'll get anywhere from 5 days to a week. And, you know, that's just the attention span of the kids, right? 5 days or a week. So we can get them launched. So anyway, we got together with him, and believe it or not, Warren says, I think there's an opportunity for you. So we got together with Orbital ATK and Virginia Space, and within a month, I was in the office of Orbital ATK, and they said, we'll do this. You know, how many of you have ever got anything accepted that quick? It was amazing. And so we ended up on the Orbital ATK second stage, and one of the things we come up with, instead of the little 50 centimeter cube, was to do the toast thing, you know, cut it up and make it in toast like this. So I don't know, any of you remember, it's called SlimSat. And we worked with Orbital ATK and Virginia Space. They've actually put a lot of money in the project. And in 2019, we launched 60 of these things for the kids. 60 in one shot, you know. And they kind of worked, but the orbit life was more like 2 days than 5 days. But it was good. And then 2021, we launched 30 of these things for the kids. So the proof is you can do it. You can make a satellite, and you can make it work in something like that. So what Nick and I decided to do was, how many of you in here consider you're techies? How many consider that you're non-techies? Okay, I want to only talk to the non-techies, all right? The rest of you guys, plug your ears. We want to offer only to the non-techies the opportunity to build a satellite with a bunch of kids. We can put these kits together, and Nick and I will sponsor at least the first 10, all of the cost for doing this. So this is a model of the satellite. It's made out of styrofoam. The batteries run down very quickly. The electronics in it don't work worth a darn, because there are none in it. And what we want to offer to you is the opportunity to get a group of kids together. And here's what our plan is. So Nick and I, along with you, would like to see younger AMSAT members. How many kids do we have in the audience here? Kids. Oh boy, I'm glad you still consider you're a kid. So we want to find a way to get new AMSAT members. So the following is, we're going to offer 10 prototype satellite kits at no charge for extensive use on the ground, but also will evolve into a space satellite to be launched into LEO off the ISS and operate below the ISS, so it has a short life. The kit will challenge you at your hometown to recruit a group of at least 10 young men and ladies and adults that want to learn the principles needed to build and operate a small picosat for at least a 3-year program, because it's going to take that long by the time you go through everything and we get our launch. So Nick and I will provide you with a kit and all of the hardware, software, and technical support to launch, to evolve into a NASA launched satellite. We call it SlimSat because this other one was called ThinSat, and we wanted another name. So anyway, what we can do is in the space of a 3U, we can put about 20 of these. And so to get the free kit, you must, now this is for all of the non-techies, you must pledge to be a member, a mentor for these program for at least 3 years. So I've got this form that I'll hand out, and you've got to complete the form. And what you'll do is on this form, you'll give me your name, signature, address, and everything, and give it to Nick and I. I have 2 copies in there, so you keep one. And I'm going to give you the kit. The kit has the foam sat in it. Now, I make models in my shop, and this isn't perfect, but it's something to show the kids. The other part of the program is we're challenging as many people as possible to give us a new name. So we get to name the class of satellite, but you can name anything that you want to on your particular satellite. So Nick has showed you the hardware. That works. But the real value of this thing is you can do lots of things with that before you actually launch it into space. And we really want to see kids here. Now, one of the things in this is you're required to get the new members of your club to get their novice license within 3 months. Okay? You think they can do that? I think so. The other thing that we're going to ask, and this might rub a few, I won't tell you what, but we want to challenge AMSAT that every one of those kids that get their novice license and staying in this club gets a free 1-year AMSAT membership. Is that possible? Let me see a show of hands who think it's possible. Ah, that's a good number. Now, what we hope is each year after this year, when we come here, we've got kids in the audience. Are you having any trouble getting kids into AMSAT? Let me show you, see a show of hands. Yeah. And that's what this program is for. So please, non-techies, we don't have as many non-techies as I'd like to see here. And if you think you're a techie and would like to do this, we will lower the standards and give it out to some of you techies. So, what I want to see is I want to see a raise of hands who would like one of these 10 kits. Nobody. Oh, 1, 2, 3. Let me 4. Okay, now we'll let the techies in. Any techies want a kit? Okay, well, we've got some people that want to do this. I would like to see more of you guys involved with the kids. But I've got these kits up here. I got 10 kits, and one of the things to give the to give the students as a reward, we've got a little duck in there, okay? Do you know why we're using ducks? Well, I'll tell you the story. We're working with a group of students who are going to do zero-G experiments on the NASA zero-G airplane. And the pilot and the co-pilot, when they decide that they're in 0G, is they have a duck, a little yellow duck that they hold up and it floats around. So we've decided that's a good mascot, is a little yellow duck. So along with the model and the guarantee that we'll support you are 10 yellow ducks for the students. So, okay, so anybody that wants to pledge and do this, please come up and get a kit. Thank you.
And Nick, we do have some time for questions. If anybody has questions, maybe about 5 minutes. If you would wait till I come around with a microphone, and then we can ask your question.
Nick, I saw a mention of a receiver. Can you telecommand to these SlimSats to control them in orbit?
I don't quite understand your question. The receiver of the ground station.
The receiver, once it's in space, can you send telecommands to it to control it?
Yeah. It's a two-way module, and it can take commands, and we're leaving it up to the designers to do what they want with it. But after watching Thompson's deal, we can probably fly his software on that if they want to. Yes.
Yeah, Nick, thank you and Bob for a wonderful presentation. And I'm wondering, so these are deployed from a 3U CubeSat, and then is that how this works? And are they tethered? Are they free fly?
No, we're gonna put them in a 3U, and we're gonna release them. Now, of course, we have the challenge with NASA to fly smaller than a 1U, but we think we'll get them to relax that rule.
Okay, and then I couldn't figure out if I was a techie or a non-techie, so I couldn't figure out if I should raise my hand. I may still do so. Thanks.
Yeah, I'm a non-techie, so probably what you're looking for. But one of the things I've been thinking about, which I've not been able to implement, is approaching parent groups and trying to get some information to them about how learning the skills that you're producing would get their kids jobs later on. In other words, sort of be an advocate for the aerospace industry. Because a lot of people, parents, even the kids don't understand that. But it might be attacking the parent group, if you can do this, like homeschoolers, that might be a possibility. I haven't done it, but to me, there's a lot of people there.
Well, we're open to talk to anybody, and the homeschoolers tend to be a pretty good place to get there.
Hey there, a couple of things. First of all, do you have any literature or proposals that I could throw at that I could give to an educator? Because I don't want to take a kit, but because I'd like to know if I can find an educator that's interested. Then we'll talk. Question number 2. So first, I'll answer that one more.
We don't have literature yet. Our main focus is we've got to get a lot of requests in by mid-November, but we will produce literature to introduce to the school system.
Okay. Question number 2. Since this is a potential swarm of small satellites being pushed out of the ISS or out of a CubeSat at the same time, are they all going to have the same frequency? And for both receivers and transmitters, and how does that work from a command or a data download standpoint if they're all running on the same frequency?
Well, we haven't quite worked that out. First of all, we can put individual address headers on the radio, but we hadn't quite worked that out yet. But that's we're going to leave that up to our students at at the university. We also would like to make a self-organizing mesh network. That's in the works too. Somehow or another these things get out there and they'll, and I see Ron shaking his head, and I'm hoping he's got ideas how to do it. But that's on our list, a design list to do.
And I think we have time for one more question.
Okay, guys, I enjoyed coming. Come participate with us.
Thank you very much, Nick and Bob. We're really grateful to see you here today.